students and friends. I am E. Satish. I am working as an assistant professor in the Department of Electronics and Instrumentation Engineering in Erode Sengundar Engineering College. Today I am going to share my knowledge about electrical machines. This is the terminal objective of the topic. At the end of the session, you will be able to clearly explain DC generator and DC motor. These are the topics today I have to discuss. Topic 1, Introduction of DC machine. Topic 2, Construction of DC machine. And topic 3, Working principle of DC generator and EMF equation. And then working principle of DC motor and torque equation. Finally, total losses in a DC machine. Next, we see the introduction of electrical machines. First, we see machine. What is meant by machine? A machine is a thing that is created by people to make work easier. It is a tool or invention which multiplies the effect of human effort. The main purpose of a machine is to make things easier for people, like lifting and moving objects around, working out a mathematical equation, or even ordering food from a restaurant. For example, this coffee maker, you show that animation image. Okay, this is one of the machine. Then we see electrical machine. In electrical machine is link between an electrical system and a mechanical system. Conversion from mechanical to electrical, that is called generator, and conversion from electrical to mechanical, that is motor. In general, the machines which are operated in relation with electrical energy are called electric machines or electrical machines. In electrical machines, either input or output or both can be electricity. In electrical engineering, electric machine is a general term for machines using electromagnetic forces such as electric motors, electric generators, and others. An electric generator is an electrical machine which converts mechanical energy into electrical energy. A generator works on the principle of electromagnetic induction. It states that whenever a conductor moves in a magnetic field, an EMF gets induced within the conductor. This phenomenon is called as generator action. An electrical motor is an electrical machine which converts electrical energy into mechanical energy. When a current carrying conductor is placed in a magnetic field, the conductor experiences a mechanical force, and this is the principle behind motoring action. Then we see some basic laws are used to study the electrical machines. First, we see Maxwell's corkscrew rule. This law says the direction of rotation gives the direction of the magnetic field. That is, hold the corkscrew in your right hand and rotates it in clockwise in such a way that it advances in the direction of current, then the direction in which the hand rotates will be the direction of magnetic lines of force. Then next we see the Fleming's left hand rule. In Fleming's left hand rule, the center finger or middle finger refers, that is represents the electric current. The thumb finger represents the direction of the magnetic force, and the forefinger represents the magnetic field. The application of the Fleming's left hand rule is the direction of the magnetic field inside the solenoid is determined by right hand thumb rule. And the Fleming's left hand rule is used to determine the direction of magnetic force. So this rule is used in motor action. Okay. Then we see the Fleming's right hand rule. In Fleming's right hand rule, the center finger or middle finger represent the induced or generated current within the conductor, and thumb finger represent the direction of the motion of conductor, and the forefinger represent the field. The application of Fleming's right hand rule is the direction of induced current within an electric generator is determined by Fleming's right hand rule. And this rule is used to determine the direction of induced current. Next we see the Faraday's law. The Faraday's law of electromagnetic induction, the instantaneous EMF induced in a circuit is directly proportional to the time rate of change of the magnetic flux through the circuit. You see that picture that clearly says that. Okay. Next we see the Lenz's law. It states that an induced current always flows in a direction such that it opposes the change which produced it. Now we see the picture 1 says when the N pole of the magnet is moved towards the coil, end of the coil becomes N pole. And when the N poles of the magnet is moved away from the coil, end of the coils becomes S pole. That is figure 2 says. Next, we see the types of DC machine. Generally, the DC machine are divided into the two parts. One is the DC generator, another one is DC motor. In DC generator, the mechanical energy is converted into the electrical energy, that is generator action, and electrical energy is converted into the mechanical energy, that is motor action. These are the classification of DC machine, and then are types of DC machine. Next we see the DC machine. First we see the DC generator. The DC generator converts mechanical energy into an electrical energy. You see one animation image, that is the turbine. The mechanical input is given to the turbine, and the turbine produces the electrical energy, that is showed by one bulb. Okay, you see that. Next we see DC motor. DC motor converts electrical energy into mechanical energy. For example, electric fan, that is electrical input is given to the fan, the mechanical energy is produced by the fan. Okay, then the construction of DC machine, that is motor or generator. Then the basic parts of DC machine are the commutator, cooling fan, carbon brushes, frame, stator winding, shaft, air gap, armature winding and armature. Then this image shows the clear parts of DC machine. The outer surface of the machine is yoke or magnetic frame or body, and then pole is divided into the two parts. One is pole core, another one is pole shoe. Then the field winding is wound on the pole core, and then commutator. The commutator then shaft. These are the main parts of DC machine. Then construction of DC machine. Okay, next we see the theoretical diagram of DC machine construction. The DC machine can be classified into two types, namely DC motors as well as DC generators. Most of the DC machines are equivalent to AC machines because they include AC currents as well as AC voltages in them. The output of the DC machine is DC output because they convert AC voltage to DC voltage. The conversion of this mechanism is known as the commutator. Thus, these machines are also named as commutating machines. DC machine is most frequently used for a motor. The main benefits of these machines include torque regulation as well as easy speed. The applications of the DC machine is limited to trains, mills. For example, underground subway cars as well as trolley may utilize DC motors. In the past, automobiles were designed with DC dynamos for charging their batteries. Then the construction of DC machine can be done by using some of the essential parts like yoke, pole core, pole shoe, pole coil, field coil, armature core, armature winding, otherwise conductor, commutator, brushes and bearings. Some of the parts of the DC machine is discussed below. Another, first we see the yoke. Another name of a yoke is the frame. The main function of the yoke in the machine is to offer mechanical support intended for poles and protects the entire machine from moisture and dust particles. The materials used in the yoke are designed with cast iron or cast steel, otherwise rolled steel. Next, pole core and pole shoe. The pole of the DC machine is an electromagnet and the field winding is winding among pole. Whenever field winding is energized, then the pole gives magnetic flux. The materials used for this are cast steel, cast iron, otherwise pole core. It can be built with the annealed steel laminations for reducing the power drop because of the eddy currents. Then pole shoe. The pole shoe in the DC machine is an extensive part as well as to enlarge the region of the pole. Because of this region, flux can be spread out within the air gap as well as extra flux can be passed through the air space toward armature. The materials used to build pole shoe is cast iron, otherwise cast steel, and also used annealed steel laminations to reduce the loss of power because of eddy currents. Then field winding. In this, the windings are wounded in the region of pole core and named as field coil. Whenever current is supplied through the field winding, then it electromagnetics the poles which generate required flux. The material used for field winding is copper. Then armature core. Armature core includes a huge number of slots within its edge. The armature conductor is located in these slots. It provides the low reluctance path toward the flux generated with the field winding. The materials used in this core are permeability, low reluctance materials like iron, otherwise cast. The lamination is used to decrease the loss because of the eddy current. Next we see armature winding. The armature winding can be formed by interconnecting the armature conductor. Whenever an armature winding is turned with the help of prime mover, then the voltage as well as magnetic flux gets induced within it. This winding is allied to an exterior circuit. The materials used for this winding are conducting material like copper. Then commutator. This is the commutator. The main function of the commutator in the DC machine is to collect the current from the armature conductor as well as supplies the current to the load using brushes and also provides unidirectional torque for DC motor. The commutator can be built with a huge number of segments in the edge form of hard drawn copper. The segments in the commutator are protected from the thin mica layer. Next we see the brushes and bearings. Brushes. The brushes in the DC machine gather the current from the commutator and supply it to the exterior load. Brushes wear with time to inspect frequently. The materials used in brushes are graphite, otherwise carbon, which is in rectangular form. Okay. Then this is the yoke. Or magnetic frame. It acts as a protecting cover for the whole machine and provides mechanical support for the poles. It carries the magnetic flux produced by the poles. This is the yoke diagram. Okay. And it is laminated by cast iron or cast steel or rolled steel. Okay. Then we see the pole. The pole is divided into the two parts. One is the pole core and another one is pole shoe. The second picture shows the field winding. This is the pole shoe and this is the pole core. The field winding is wound on the pole core. Okay. Then next we see the armature core. This is the picture of armature core. These are the slots. The conductor are placed in the slots and air holes and laminations keyway slot. Okay. Next we see the armature winding. In armature winding, the conductors are placed in the armature slot, and this is the winding are wound on it. And then commutator. The commutator is used to convert the alternating EMF to unidirectional EMF. Okay. This is the image of commutator. Next we see the brushes and bearings. The brushes, which are made up of carbon or graphite, it collects the current from the commutator and to convey it to the external load resistance. They are rectangular in shape. These brushes are housed in brush holders and mounted over brush holder studs. The brush holder studs are mounted on the brush yoke or rocker arm. The brush holder studs are insulated from the brush yoke by insulation sleeves. Then we see the bearings. The bearings are usually employed as they are reliable for light machines. For heavy duty machines, the roller bearings are used. The bearings are packed in hard oil for quicker operation. Next we see the difference between lap winding and wave winding. In lab winding, the number of parallel paths equal to poles, that is A equal to P. In wave winding, the number of parallel paths equal to 2, that is A equal to 2. Second point, in lab winding, number of brushes sets required is equal to number of poles, and in wave winding, number of brushes sets is always equal to 2. Third point, for lab winding, preferable for high current low voltage capacity generators, and in wave winding preferable for high voltage low current capacity generators. And then in lab winding, normally used for generators of capacity more than 500 amps, and in wave winding preferred used for generators of capacity less than 500 amps. This image shows the connection of lab winding and wave winding. This is the construction of DC machine image. Okay. Armature, commutator, shaft, all are here. Okay. Then is the rotor part, and then this image says in a generator, the mechanical input is given to the machine, and the machine produces the electrical output, that is called generator. In motor, the electrical input is given to the motor, that is showed here, and then mechanical output is produced by the machine. This is the motor. And now we see the construction of DC machine. You see one small video by using the below link, or double click their image. This
DC
image.
generator.
See it.
We know that a DC generator uses electromagnetic induction to convert mechanical energy into electrical energy. It is frequently used in houses and offices. But do you know how it is constructed? Let's try to understand this. A DC generator consists of a magnetic frame or yoke, the pole core, the pole coils or field coils, the armature core, the armature windings, the commutator, the brushes, and the bearings. Out of these parts, the pole core, the armature core, the yoke and air gaps between the poles and the armature core form the magnetic circuit. Let's briefly describe each of these components. Yoke is the outer frame of a DC generator which serves two purposes. It acts as a protecting shield for the generator and provides mechanical support for the poles. In small generators, where cheapness rather than weight is the main consideration, yokes are made of cast iron. But for large generators, yokes are usually made of cast steel or rolled steel. Field magnet consists of the pole core and the pole shoes. It basically spreads out the flux in the air gap. Since it generally has a large cross section, so it reduces reluctance of the magnetic path. It acts as a support for the field coils. Pole coils consist of the copper wire or strip which is wounded on the former. After getting the correct dimensions, the former is removed and the wound coil is put into place over the core. When current is passed through these coils, the poles get electromagnetized and produce the necessary flux that is cut by revolving the armature conductors. Armature core houses the armature conductors or coils and causes them to rotate, cutting the magnetic flux of the field magnet. It also provides a path of very low reluctance to the flux through the armature. It is cylindrical or drum-shaped and is built up of usually circular sheet steel discs or laminations approximately 0.5 mm thick. The slots are either die-cut or punched on the outer periphery of the disc, and the keyway is located in the inner diameter. Armature windings are mostly employed for the armature of a DC machine. They are of two types: lap windings and wave windings. The difference between the two is merely due to the different arrangement of connections at the front or commutator end of the armature. In lap winding, the number of parallel paths is always equal to the number of poles and also the number of brushes. It is suitable for high current, low voltage machines like welding plants. Whereas in wave winding, the number of parallel paths is always 2, and there may be 2 or more brush positions. It is suitable for high voltage, low current machines like generators used for lighting. Commutator facilitates the collection of current from the armature conductors and converts the alternating current induced in the armature conductors into unidirectional current in the external load circuit. It is of cylindrical structure and is built up of wedge-shaped segments of high conductivity, hard-drawn or drop-forced copper. The segments are insulated from each other by thin layers of mica, and the number of segments is equal to the number of armature coils. Brushes collect current from the commutator. They are usually made of carbon or graphite and are in the shape of a rectangular block. They are housed in the brush holder, which is mounted on the spindle. These brushes can slide in the rectangular box, which is open at both the ends. A flexible copper pigtail mounted at the top of the brush conveys current from the brushes to the holder. The number of brushes per spindle depends upon the magnitude of the current to be collected from the commutator. And ball bearings are frequently employed because of their reliability. The ball and rollers are generally packed in hard oil for quieter operations. Note that sleeve bearings are used in order to reduce bearing wear. Basically, the schematic diagram of a DC generator is as shown, and its main parts are
Okay. Next, we see the principle of operation of DC generator. That is working principle of DC generator. Okay. When a conductor is rotated or moved in a magnetic field in such a way that it cuts the magnetic lines of flux, then EMF is induced in the conductor according to the Faraday's law of electromagnetic induction. The direction of induced EMF is given by Fleming's right hand rule. This EMF causes current to flow if the conductor circuit is closed. This EMF is alternating in nature. This alternating EMF is converted to unidirectional EMF by commutator and supplied to the external load by using the brushes. That is the motion input, that is the mechanical input is given to the machine, and the electrical output, that is EMF, is get from the machine. Generator action, the direction of induced EMF is using the Fleming's right hand rule. Then we already discussed, so we move to the next slide, that is the principle of operation of DC generator diagram by using the slip rings. Let us the difference between the AC motor and the DC motor includes the following, that is working of DC generator with the slip rings. Let us consider a single turn coil, that is ABCD, rotated on a shaft within a uniform magnetic field of flux density. It is rotated in an anti-clockwise direction. Let L be the length and B be the breadth of the coil in meters. When the coil sides AB and CD are moving parallel to the magnetic field, the flux lines are not being cut and no EMF is induced in the coil. At this position, we assume the angle of rotation theta as 0. This vertical position of the coil is the starting position. According to the Faraday's law, the EMF induced is proportional to the rate of change of flux linkages, that is equal to E equal to minus N into d pi by dt, where N is the number of turns and pi is the flux and t is the time. As N equal to 1, so E equal to minus d pi by dt volts. Initially, when the coil is moving parallel to the flux lines, no flux lines is cut and hence d pi by dt equal to 0 and EMF is also 0. After time t seconds, the coil would have rotated through an angle omega t radians in the anti-clockwise direction. The flux then linking with the coil is BLB cos theta. When theta equal to 90 degree, the coil sides are moving at right angles to the flux lines. The flux lines are cut and at the maximum rate and the EMF induced is maximum. When theta equal to 180 degree, this is the maximum flux induced by the machine. Okay. When theta equal to 180 degree, this is the position of 180 degree. This is the position of 180 degree. The coil sides are again moving parallel to the flux lines. AB and CD have exchanged positions and the EMF induced is 0 once again. Where theta equal to 270 degree, the coil sides again move at right angles to the flux lines but with their position reversed when compared with theta equal to 90 degree. Hence the induced EMF is maximum in the opposite direction. When theta equal to 360 degree, the coil sides once again move parallel to the magnetic field, making the induced EMF equal to 0, the coil has now come back to the starting point. If the rotation of the coil is continued, the changes in the EMF are again repeated for the two-pole generator shown. One complete cycle of changes occurs in one revolution of the coil. The changes in voltage E with respect to the angle of even time can be plotted as shown in figure. The EMF changes from instant to instant and becomes alternately positive and negative. Such an EMF is called an alternating EMF. If the coil sides are connected to two slip rings A and B and an external resistance R connected across them, a current flows through the resistor which is again alternating. The induced EMF in the coil can be increased by increasing the flux density B and increasing the angular velocity omega. In commercial generators, a large number of coils are used and they are housed in the armature which rotates on a shaft at high speed. The current flowing in the external resistance to a DC generator is made unidirectional by replacing the slip rings by a split rings. Now see the split rings diagram. This is the position 1. This is the position 1, that is a 0, theta equal to 0 degree. Then this is the theta equal to 90 degree. The maximum flux is produced by the machine because the maximum flux can be cut by the coil or conductor. So the EMF is high. So at this position 180 degree, the coil is parallel to the flux lines. So no EMF is cut by the conductor. So then this is the position of 270 degree. The maximum EMF is induced, same as in the theta equal to 90 degree, but it is in the opposite direction. Then this is the position of 360 degree. No EMF is induced because no EMF is cut by the coil or conductor. So now this is the principle of operation of DC generator by using the slip rings. On animation image, the coil is rotated in the conductor in the flux lines. Coil or conductor are rotated in the flux lines. So the coil or conductor cuts the magnetic flux lines. Based on the magnetic flux lines cuttage, the EMF will be generated, that is shown by this meter. Okay, next we see the principle of operation of DC generator, slip ring diagram. Another one image, animation image for this operation. The coil or conductor rotated in the magnetic flux lines. So the magnetic flux lines are cut by the conductor or coil. So this is the graph waveform. Okay. So next we see the split ring diagram. Okay. Split ring. The current flowing in external resistance to a DC generator is made unidirectional by replacing the slip rings by a split rings. Here we using the split rings. Okay. the coil sides A, B, C, D, split rings is used here, and one external resistance also connected here. Okay, the slip rings is split, the ring is split into two equal segments, that is, one is P, another one is Q, or one is E, another one is H, and the segments are insulated from each other and also from the shaft. The coil side AB and the coil side AB is always attached to the segment E, and likewise CD is connected to Q. It is indicated in figure. The brush B1 and B2, the brush B1 and B2, that is in 1 and 2, touch these segments and are meet to collect the current. During the first half revolution, current flows along AB, FG, CD through brush B, which is positive, and into B2, that is in figure. After half a cycle, AB and CD have exchanged positions along with the segments E and H, and current now flows through DC, G, F, BA. B1 is now in contact with Q. For each half revolution, the positions of segments P and Q also reverse. Hence, the current in the load is always unidirectional. The change over a segments E and H takes place when flux linkage or induced EMF is maximum in a generator. The split rings are called commutator. Okay, this is the split ring. Okay, one full image. Next we see the split rings generator operation. Here this is the split rings, clear picture. Then on coil, this is the carbon brush is connected in the split rings. Electrical input is given to the machine. Then on animation image, sorry, here one load is connected here. Load is connected here. Now we see the on animation image, that is the coil is rotated in the magnetic flux lines. Here the split rings is connected in the coil. So the alternating EMF is converted into the unidirectional EMF by using the split rings. Okay, that is shown the meter. So this is the waveform. Next we see the one video for principle of operation of DC generator by using the below link, or you touch this image.
How do power stations provide electricity to thousands of houses around a city? They don't use giant batteries. They do that by spinning a giant turbine like this. And to spin such a turbine, some power stations use very hot steam that blows over the turbines and spins it. Or maybe we can use the energy of the falling water. Or another example could be We fit these inside giant windmills and let the wind do the work for us. Whichever way you choose, all we do is spin a giant turbine. But how does turning something create electricity? Well, the technology is based on electromagnetic induction, discovered by Michael Faraday more than 200 years ago. The basic idea is that if you take a wire and move it up or down inside a magnetic field, it induces an electric current. So all we have to do is attach a coil of wire to these giant turbines and place them inside a magnetic field. As the turbine rotates, the coil starts rotating and the wires start moving up and down inside the magnetic field. That produces the electric current. And this can now be used to light up things. These devices are called electric generators. They convert spinning or mechanical energy into electrical energy. So let's look at them in detail now. So let's start by figuring out in what direction a current gets induced or generated in this coil once it starts rotating. So let's say, in our example, the coil rotates clockwise, somewhat like this. Now, how do we figure out the direction of the induced current? Well, we have already learned something called the Fleming's right-hand generator rule, which says you stretch the fingers of your right hand like this such that they are perpendicular to each other. Then the thumb represents the direction of the motion of the wire, that is the direction in which you are pushing the wire. The forefinger gives you the direction of the magnetic field. Then our middle finger will give us the direction of the current. So all we have to do is align our right hand to make sure the thumb and the forefinger point in the direction of the motion and the magnetic field. Then the middle finger will give us the direction of the current. So let's use our right hand rule on the pink wire that is going upwards, as you can see, and on the blue wire that is moving downwards. So it'll be a great idea if you can first see whether you can try this yourself. So go ahead and use your right hand and see if you can figure out the direction of the current in the pink and the blue wire. Alright, if you've done it, let's first start with the pink wire. Because the pink wire is going up, the thumb should be pointing upwards. The magnetic field is to the right, so the forefinger should be pointing to the right. And so if we align our fingers that way, it will look like this. Since the middle finger is pointing inwards, this means the current in the pink wire must be inwards. Similarly, for the blue wire is moving downwards. So the thumb will be pointing down, the forefinger will still be pointing to the right. And so if we arrange our right hand over here, it will look like this. The middle finger is pointing out of the screen. That means the current in the blue wire will be coming out of the screen. So what we have seen is if a wire is moving upwards over here, then the current will be into the screen. And if the wire is moving downwards, then the current will be out of the screen. Remember this will be important. So now let's get rid of the hands and put arrow marks to indicate the current. And now we can guess what direction the current will be in the rest of the wires. Since the current has to flow from the pink to the blue, we can say that the current has to move here like this. And then the current has to move here this way. It goes out. It goes to that external circuit, maybe where there is a bulb. We'll look at that later. Then the current comes back like this and it flows in this way. And the current continues to flow like this as the coil keeps rotating. Because you can see the pink wire is still going up and the blue wire is still going down. Until we come to this point. Because now the pink wire starts moving downwards. And now the blue wire starts moving upwards. Can you see that? Again, if I go back and come back again, notice the pink wire is coming down and the blue wire is going up. This means now the current in the pink wire should be out of the screen. Because we already saw using our right hand rule. When the wire is going down, the current must be out. And in the blue wire, which is going up, the current must now be inwards. In other words, the current will now change its direction. This is the important thing. So the current changes its direction and it continues to flow this way until again the pink wire comes on the left side. Because now again, the pink wire starts going up, the blue wire starts going down, and as a result, the current in the pink wire will be inwards, the current in the blue wire will now be outwards, the current will again reverse. So every time our coil is in this position, which is perpendicular to the magnetic field, we will see that the current direction will flip. And so if you look at the entire animation now, it looks somewhat like this. Every time the coil comes in this position, perpendicular to the magnetic field, the current direction keeps changing. Now, of course, in the animation, I'm pausing the animation when my coil is perpendicular to the magnetic field so that we can see the current flipping its direction. But of course, in reality, the coil will be pushed continuously. There will be no stopping. There will be no jerking motion like we are seeing over here. Now, the next question we might have is how do we connect this coil to an external circuit, let's say to a bulb? Well, we could connect it directly, right? Let's see what happens if we connect the circuit directly. Current will flow, no problem. But as the coil starts rotating, notice the wires start twisting and tangling and turning and whatnot. That's going to be a problem. So to avoid that, we will not connect the wires directly. Instead, we will use an arrangement involving brushes and slip rings. It looks somewhat like this. So basically we have two metallic rings, a pink one and a blue one. And what we may not make out from my diagram over here is that each ring is connected to one wire only. So the pink ring is only connected to the left wire, and the blue ring is only connected to the right wire. And these wires are connected to carbon brushes, which is also conductor, and they are just touching these rings so that there is a metallic contact, but they're not stuck to it. So right now, there is a contact, the circuit is complete, and as a result, the current comes out of the blue ring, as you can see, moves this way, and current flows into the pink ring and goes like this. And when the coil starts rotating, as you can see, the rings rotate along with the coil. But since the brushes are not stuck to the rings just slip through the brushes. That's why they're called brushes. As a result, the brushes will not rotate. That solves the problem of wires twisting and tangling. And all the while, an electric contact is rotating. Now, once our coil comes in this position, we've seen that the current reverses. So now, the current will flow out of the pink ring, goes like this, through the bulb, and now enters into the blue. So for every half a rotation, the current through the bulb also reverses. Let's say when the current is flowing this way, the bulb glows blue. And let's say when the current reverses, it flows like this, the bulb will glow yellow. And so now if you look at the entire animation, it looks somewhat like this. And so we have successfully built our generator. And what's interesting to see is that the current from that generator is continuously changing its direction. Such a current is called alternating current, or AC. And this might sound a little weird, but it turns out that when you want to transmit electricity over a long distance, like from the power station to your houses, then alternating currents, or AC, have some great advantages over unidirectional currents, or DC. And it's for that reason, the current that we get at our houses, the electricity that we get at our houses, are all AC. And these generators are called AC generators. Finally, what if you want to build a DC generator, where we don't want the current direction to change? We want it to remain the same throughout. Let's say in this direction. How do we do that? Well, to build that, first let's get rid of these rings. Alright, now to make sure that the current direction remains the same, what we will need is that these brushes to continuously keep changing contacts between these wires for every half a rotation. Let's see why. So if I want the current to flow this way, right now in this position, I can connect this brush to this wire, so the pink side, so that the current flows like this and comes out. But as the coil rotates, notice once it comes to this position, we've seen that the current starts flipping, the current reverses. And so now, to maintain the current in the same direction, we would now require this brush to come in contact with this wire. That is the blue side, right? And then again, once we come to this position, again it flips, the current flips, and again we would want now this brush to come in contact with this side. And so as a result, can you see that for every half a rotation, we would want the contacts to keep changing. But how do we make sure that happens automatically? We can do that by attaching split rings. Split rings, as the name suggests, is a ring that is split in between, giving two half rings with some gap in between. Now let's see how this arrangement automatically changes contact for every half a rotation. So right now, this brush is in contact with the pink side. But as the coil rotates and comes to this position, the current reverses. And now notice the brush is in contact with the blue side, making sure the current still flows in the same direction through the wire. Again, as the coil comes to now this position, finishing another half a rotation, again notice it has changed contact. It is now in contact with the pink ring, connected to the pink side. In this way, we have now built our DC generator, where the current only flows in one direction through any external circuit. And this arrangement, which helps us automatically change contacts, we call them as commutators. So split rings act like commutators. So to summarize what we learned, if you take a coil and spin in a magnetic field, then due to electromagnetic induction, a current gets generated in that coil. Now the direction of the current depends on whether the wire is going up or whether it's going down. And as a result, for every half a rotation, we see that the direction of the current keeps changing. And so this generator is called an AC generator because it generates an alternating current, a current whose direction keeps continuously changing. On the other hand, if we use split rings, then it acts like a commutator. It keeps changing the contacts for every half a rotation and makes sure that the current does not change direction in the external circuit. We call this a DC generator. And so this is how we can generate electricity just by rotating a coil in between a couple of magnets.
Okay, that video shows everything. So then we see the generated EMF or EMF equation of a generator. So this in this slide, derive the expression for the EMF equation generated by the DC generator. Let pi be the flux or pole in Weber. Z indicates total number of armature conductors, and P is the number of poles, and A is the number of parallel paths. That is A equal to 2 for for wave winding, and A equal to P for lab winding, and N is the speed of armature in RPM, and Eg is the EMF of the generator, that is equal to EMF per parallel path. First, flux cut by one conductor in one revolution of E armature equal to that is d phi by dt. That is the flux cut by one conductor in one revolution, that is equal to d phi equal to phi p or b phi. Okay. That is the generated EMF Eg equal to generated EMF generated in any one of the parallel paths. That is the average EMF induced per conductor or average EMF generated per conductor equal to d phi by dt volt. Okay. Now flux cut by conductor in one revolution, that is d pi equal to pi p Weber. Okay. Then the number of revolutions per second equal to n by 60. Time taken for one revolution dt equal to 60 by n. According to the Faraday's law of electromagnetic induction, the EMF generated per conductor equal to d pi by dt that is equal to pi p n divided by 60 volts. Okay. Now the number of conductors in one parallel path equal to z by a. So EMF generated per path equal to pi p n divided by 60 into z by a volts. The generated EMF Eg equal to phi z np divided by 60 a volts for wave winding phi z np divided by 120, and for lab winding phi z n divided by 60. Okay, this is for lab winding. Okay, then we see the applications of DC generator. The DC generator is classified into the two types. One is the separately excited DC generator, another one is self-excited DC generator. In separately excited DC generator, accurate supplies for testing labs and World Leonard speed control system. And then self-excited DC generator is further classified into the three types. One is the shunt DC generator, one is DC series DC generator, another one is compound DC generator. In shunt DC generator are used in power supply, lighting and battery charging machineries, and series DC generator, arc welding supplies and line voltage booster for DC system, and compound DC generator, lighting, arc welding, heavy service like railways, line voltage booster for DC system. Then now we see the principle of operation of motor. There is DC motor. The electrical input is given to the machine and the mechanical output is produced by the machine. That is, the current input is given to the machine and the motion output is get from the machine. When a current carrying conductor is placed in a magnetic field, then the conductor experiences a force according to Lorentz law. This law states that the total force acting on a charged particle due to electric and magnetic fields is equal to the sum of the electric and magnetic forces acting on it. The direction of force experienced is given by Fleming's left hand rule. In a DC motor, the commutator helps to produce the unidirectional torque. Okay, the alternating torque is converted to the unidirectional torque by using the commutator. Okay, the main principle of the working principle of DC motor is whenever a current carrying conductor is placed in a magnetic field, it experiences a force. This is the principle of DC motor. And already we discussed what is the DC generator. That is, the whenever a conductor is placed in a magnetic field, dynamically an EMF is induced into that is the generator. In a motor, whenever a current carrying conductor is placed in a magnetic field, it experiences a force. This is the difference. Okay. Then we see the Fleming's left hand rule that is used in the DC motor action. Okay, so this is the working principle of DC motor image. Okay, magnetic flux lines are here, and then one conductor is placed in first image, and then in second image the current carrying conductor. So one flux is produced by the conductor also. So both the fluxes are opposing one side and adding one side, so that all are showed by the image. Okay, the basic principle of a DC motor is that whenever a current carrying conductor is placed in a magnetic field, it experiences a force and it tends to rotate. The magnetic field between two poles N and S is shown in figure. A current carrying conductor along with the direction of the flux loops around it is shown in figure B. If a current carrying conductor is placed between two magnetic poles as shown in the figure B, both the fields will be distorted. Above the conductor, the field is weakened, and below the conductor, and the field is strengthened. Therefore, the conductor tends to move upwards. The force exerted upwards to burn depends upon the intensity of the main field flux and magnitude of the current. Then the direction of the current through the conductor is reversed as shown in the figure. Here the field below the conductor is less and field above the conductor is more. Then the conductor tends to move downwards. The magnitude of the force experienced by the conductor in a motor is given by F equal to BIL newtons. Here the B is magnetic field intensity in Weber per meter square and I current in amperes and L length of the conductor in meters. The direction of motion is given by the Fleming's left hand rule, which states that if the thumb, fore and middle finger of the left hand are held such that the fingers, so three mutually perpendicular directions, and if the force and if the forefinger indicates the direction of the field and the middle finger indicates the direction of the current, and then the thumb finger points the direction of motion of conductor. In a DC motor, a strong electromagnetic field and a large number of current carrying conductors housed in the armature make the armature rotate. Okay, here the two fluxes are here. Okay, this is the main field flux by producing the permanent magnet, and one current carrying flux is produced by the conductor. both the fluxes are adding here, and in downside both the fluxes are opposing here, and in fourth image, that is D, figure D, that is the torque is produced here. Torque means the twisting or tuning force about an axis. This is the torque. Okay, so this is the working principle of DC motor. Here I showed some animation images and images for the clear understanding. That is this is the principle, this is the construction of DC motor. This is the coil field winding, this is the armature winding, commutator and shaft. The electrical input is given to the machine. The electrical input is given to the conductor. So the conductor produces one flux, that is the conductor produces the flux, and another one flux that is produced by the magnet. So both the fluxes are here. You see that picture I showed it. That is, the current carrying conductor is rotating in the magnetic flux lines. So the rotating force is produced. This is a mechanical energy. So you see in another image also. Okay, the electrical input is given to the machine, that is the conductor. So the mechanical output is produced by the conductor. So next we see one video using the below link, or otherwise you touch that picture. There is a double click here.
If you look around your house, you will see many devices that have electric motors, such as kids' toys, table fans, toothbrushes, hair dryers, and this electric cutting knife. But how does the electric motor work? You turn it on and somehow it starts rotating. Why is that? In this video, we'll cover the basics of electricity and magnets, and then put it all together to understand how the motor works. This video is sponsored by Brilliant. Let's start with something called a circuit. You have a battery, some wires, and a device that uses electricity, such as a light bulb. Electricity flows through the circuit, but as soon as there is a break in the wire, the electricity stops flowing and the light bulb goes off. The path must be complete for the circuit to work. This is best done through the use of a switch. Electricity is flowing down the wire. This is called conventional flow. If we take the battery out and flip it, then the current will flow the other way. The light bulb will still work in either case, but there are some devices that will work differently depending on which way the current flows. Okay, so that's the basics of a circuit. Now let's come over here. This is a magnet. It has a north pole and a south pole, and it likes to attract other metal objects like these paper clips. If you bring another magnet towards it, opposite poles attract, and the same poles repel. Magnets don't have to be in this shape. For example, some magnets might be more flat like this. You can think of this magnet as always on, it's always working, you can't really turn it off. That's why it's sometimes called a permanent magnet. It's made up of many smaller magnetic domains that are lined up in the same direction. But later I'll show you a type of magnet where this is not always the case. Let's take one of our permanent magnets and drill a hole in the center and put it on something that will allow it to spin. Now bring another magnet towards it. Our spinning magnet will immediately line up until opposite poles are right next to each other. Now switch out the side magnet. The same poles repel and opposite poles attract. If we keep switching out these side magnets, then our spinning magnet will just keep spinning. This concept of the spinning magnet is really important. We'll come back to it in a moment. Here's a metal bulb which is not a magnet. It's made up of magnetic domains, but they are pointing in random directions. Now let's take a wire, wrap it around several times, and then create a circuit. The current through the wires forces the magnetic domains to line up. That means we've just made a magnet, or more specifically, an electromagnet. It can do the same things that a permanent magnet can. It can pick up pieces of metal, and it has a north and a south pole which will attract or repel other magnets. But the electromagnet is special in the sense that it can be turned on or off, just like the light bulb. You can't do that with a permanent magnet. Now watch what happens when we flip the battery. The electric current was flowing this way, but now it flows the other way. This will cause the poles on our magnet to switch places. North will become south, and south will become north. This is called reversing the polarity of an electromagnet. Instead of flipping the battery, an easier way to do this is to just switch the wires. You should be aware that the electromagnet will get very hot if it's on for a while. Just a caution in case this video inspires any science projects. Let's come back to our spinning magnet. This time we'll replace the spinning magnet with our electromagnet. As soon as we connect the wires, the magnet turns on and it lines up with the side magnet. Now, in reality, connecting these wires will prevent the bolt from spinning freely. But what's important here is the concept of the spinning electromagnet. Now let's switch the wires to reverse the poles on the electromagnet. The same poles repel and opposite poles attract. Now reverse the polarity again. Same poles repel and opposite poles attract. If we keep switching the polarity, our electromagnet will just keep spinning. To make this stronger, let's bring in another permanent magnet on the side. Notice how this side has the south pole towards the center, and this side has the north pole towards the center. The side magnets work together to spin the one in the middle. This right here shows the very basics of an electric motor, but we need to make a few improvements. The two side magnets can be replaced with stronger curved magnets. And instead of a bolt with wires, we're going to use a metal loop. This is called the armature. Connect our wires and we have a circuit again. This time you can think of the electromagnet as flat like this with the south pole pointing up. Now the armature will spin until opposite poles are lined up. We can keep it spinning by switching the wires just like we did before. But this is a lot of work to sit here and manually switch these wires. We need to add something to the armature called a commutator. It's a ring with gaps on the opposite sides. The commutator will spin along with the armature. Now we connect the circuit with two brushes on the side. These brushes will slide along as the commutator spins, and they are spring-loaded so that they always maintain contact. The current flows from the wire, through the brush, the commutator ring, the armature loop, and back through the other side. Now we have our electromagnet and the armature spins. As we come around this time, the brushes will switch contact to the other side of the commutator ring. Remember, there's two brushes, so this is happening on both sides. Before the switch, the current in the armature is flowing this way. After the brushes switch sides, current will flow the other way. This means the electromagnet switches polarity, which will cause the armature to keep spinning. This commutator ring does the same thing as switching the wires like we were doing before, but this time it does it all on its own. It will continue to spin as long as we're connected to a battery. Disconnect the battery, no more electromagnet, and the spinning stops. Now so far we've only used one loop on the armature. This will cause our motor to have an irregular speed, and in fact, we could get stuck in this position, with the brushes halfway between commutator segments. What we can do is split the commutator ring and then add another loop. So first, the brushes are in contact with these two commutator segments, which turns on this electromagnet, which causes it to start spinning. Once we get to here, the brushes switch contact to the next pair of commutator segments, which means this loop turns off and the next loop turns on. Now this electromagnet wants to spin. The brushes switch contact and the next loop turns on. This keeps happening as our motor spins. It's almost like the loops will take turns being an electromagnet. Some electric motors will add many loops to the armature. This ensures that there will be a continuous spinning motion on the motor. This spinning force on the armature is called a torque. Stronger torque means a faster spin. There are some things we can do to improve the torque of the motor. Electromagnets are stronger when there are more wires. This is true when we wrap more wires around the metal bolt, and it's also true when each of our armature loops are made of many wires. the motor will have stronger electromagnets, which means it will spin faster. If you look at some pictures of real electric motors, you can see lots of wires wrapped around. And yes, this is the same reason. More wires wrapped around means stronger electromagnets. Another way to make this stronger is to use more electricity. Let's learn a few more terms here. The part that doesn't move is called the stator. In this case, it's the two permanent magnets on the side. These fit inside the edges of the motor case. The armature in the middle is also called a rotor. Remember, this is the part that spins. The axle goes through the middle here and then sticks out the back of the motor. What I've shown you in this video is called a DC motor. If you have a device that moves and is powered by a battery, there's a good chance there's a DC motor in it. Other types of electric motors will work a little differently than what I've shown here. No matter the type of motor, most of them will produce some type of spinning motion. Once it's spinning, we can use this to make different devices move. In this case, a kid's toy. Or even a fan that cools your room. The spinning of the motor can be converted to other types of movement, such as the side-to-side motion that we see in this fan. Or how about this electric cutting knife? Each blade is going back and forth. It all starts with the spinning of the motor to turn a gear, which then pushes these two pieces back and forth. So hopefully this video has made a few light bulbs go off in your brain. If you like learning new things, head on over to Brilliant. This is a problem-solving website and
I hope you get some clear idea about the principle of DC motor. So we move to the next topic, that is the torque equation of DC motor. In DC motor, the torque equation, okay, we already studied about we already discussed about the DC generator EMF equation, okay. That is the mechanical input is converted into the electrical output. So we see in the EMF equations, okay. So in a motor, the electrical input is converted to the mechanical output. So we studied about that is torque equation, okay. So in torque equation, the torque is nothing but twisting or tuning force about an axis. Torque is measured by the product of force and the radius at which the force acts. Consider a wheel of radius r meters acted on by a circumferential force F newtons as shown in figure. Let the force F cause the wheel to rotate at n rpm. The angular velocity of the wheel is omega is equal to 2 pi n divided by 60 radius per second. Okay. Then torque T equal to F into R. That is, torque or movement of force is the tendency of a force to rotate or move an object about an axis. A force is a push or pull. Likewise, torque is a twist to an object. Mathematically, the torque T equal to F into R, that is force into radius. Then n equal to the speed of the armature in rpm, that is n divided by 60 rps. Then work done per revolution equal to force into distance traveled per revolution, distance moved per revolution. That is, work done equal to F into 2 pi r Newton meter. Work done per second equal to F into 2 pi r into n divided by 60 Newton meter. work done equal to, that is simplified by the above equation, that is the 2 pi n divided by 60 into F into R Newton meter per second or watt. So work done equal to 2 pi n Tg divided by 60, that is generated torque. Okay, the expression for voltage in DC motor is given by V equal to EA plus IA RA. EA is armature EMF, then armature current, and RA is armature resistance. IA is armature current and RA is armature current, multiply throughout by IA. So V into IA equal to EA into IA plus IA square into RA. Okay, so the power developed P equal to, sorry, in electrical input, the electrical input equal to electrical power equivalent to mechanical power developed plus armature copper loss. Okay, the mechanical power developed, so the power developed P equal to work done divided by time, so equal to work done F into 2 pi r divided by time, that is the time for one revolution, so it is equal to F into 2 pi r divided by 60 divided by n. So this is that. So in mechanical power developed equal to EA into IA watt. So since in equation 1 and 2, 2 pi n Tg divided by 60 equal to EB into IA. So you equalize that. So 2 pi n Tg divided by 60 into pi z n EB equal to pi z np divided by 60 A into IA. So Tg equal to, you simplify it, so we get 1 by 2 pi into pi z ia into p by a. So Tg equal to 0.159 pi z ia into p divided by a Newton meter. Okay, so Eb is nothing but back EMF. So what is meant by back EMF? An interesting aspect of motoring action is while a machine functions as a motor, the conductors are cutting flux, and that is exactly what is required for generator action to take place. This means that even when the machine is working as a motor, voltages are induced in the conductors. This EMF is called the back EMF or counter EMF, since the case for this is the rotation, which in turn is due to the supply voltage. According to Lenz's law, the direction of the back EMF opposes the supply voltage. That is, EB is nothing but pi z np divided by 60 A volts. Okay. So this is the back EMF. So again I explain, that is back EMF EB into IA equal to TA into that is Tg into 2 pi n divided by 60. So EB equal to 5 z np divided by 60 A. So we get Tg, that is Tg equal to this equation by the above equation. So Tg equal to 0.159 pi z ia into p by a Newton meter. Hence the torque of a DC motor is directly proportional to the flux per pole and armature current. Next we see the application of DC motor. The DC motor is classified into the shunt, series, cumulative compound and a differential compound. Okay, in shunt motor the characteristics are speed is fairly constant and medium starting torque, and the application of the shunt motor is blowers and fans and centrifugal and reciprocating pumps, lathe machines, machine tools, milling machines, drilling machines. These are the applications of shunt motor. And the series motor, The characteristics is high starting torque, no load condition is dangerous, variable speed. The application is cranes, hoist, elevators, trolleys, conveyors, electric locomotives, and the cumulative compound motor. The characteristics high starting torque, no load condition is allowed. It is used in rolling mills, punches, shears, heavy planers, elevators. And the differential compound machine, the speed increases as load increases. Okay, this is the characteristics of differential compound motor, and the application, it is not suitable for any practical applications. It is studied only by the theoretical applications. And then now see the what are the losses, that is the total losses in a DC machine. In DC machine, the losses are classified into the three types. One is the copper losses and iron losses and mechanical losses. In copper losses, armature copper loss, shunt field copper loss and series field copper loss are there, and iron losses, hysteresis losses and eddy current losses are the iron losses, and the mechanical losses, that is classified into the friction and windage. Okay, next we see the total losses in a DC machine are copper, iron and mechanical losses. In copper, losses is mainly due to the current passing through the winding. Okay, so the armature copper losses is the 30 to 40 percentage of full load losses. Okay, in shunt field copper losses 20 to 30 percentage of full load losses, and series field copper losses also there in the copper losses. So armature copper losses equal to Ia squared into Ra. So Ra equal to the armature resistance and Ia is the armature current. The losses due to brush contact resistance is usually included in the armature copper losses. And now see the shunt field copper losses, that is ISH shunt field. So ISH squared into RSH. So RSH is the shunt field resistance and ISH is the shunt field current. In series field copper losses, ISE square into RSE. So RSE equal to series field resistance and ISE equal to series field current. Okay, next we see the iron losses. So iron losses are classified into the two types. One is the hysteresis losses, another one is the eddy current losses. In iron losses, 20 to 30 percentage of full load losses. Okay, so in hysteresis losses, the losses is due to the reversal of magnetism of the armature core. Every portion of the rating core passes under N and S pole alternatively. Thereby attaining S and N polarity respectively. The core undergoes one complete cycle of magnetic reversal after passing under one pair of poles. P equal to number of poles and N equal to the number of speed in RPM. So the frequency of magnetic reversals F equal to NP divided by 60. This is the hysteresis loss. So then we see the eddy current loss. When the armature core rotates, it cuts the magnetic flux. Hence, an EMF induced in the body of the core according to Faraday's law of electromagnetic induction. This EMF through small sets up large current in the body of the core due to its small resistance. This current is known as eddy current. These core laminations are insulated from each other by a thin coating of varnish due to the core body being one continuous solid iron piece. The magnitude of eddy current is large as armature cross-sectional area is large. Its resistance is small, hence eddy current losses is large. In figure, the same core has been split up into thin cross section, very high resistance, hence magnitude of eddy current is reduced considerably thereby reducing eddy current losses. Eddy current losses is reduced by laminated core, but hysteresis loss cannot be reduced by this way. Okay. So next, this is the mechanical loss that is classified into the two types. One is the friction losses, another one is the windage losses. In friction losses, the friction losses due to bearings and windage losses due to air gap between armature core and pole shoe. Okay, so this is the total losses. So now the question and answer. If you have any queries, you followed by the comment section. Okay, now okay, thank you.